for me. Yeah, only at that part, I think.
Okay, so I think it's better, unless this is a general question, I think it's better if we resolve it in private. So maybe we can set an appointment and we can have a chat via Zoom, me and you, and I can explain it again. Okay.
Oh yeah,
because
it's okay.
yeah,
I mean, yeah.
so I think it would be, unless everybody has the same question. If you all have the same question and you want me to explain again the central limit theorem, then I can go back there. Otherwise, I think it's better if we just do it. Anyway, the thermodynamic limit is the limit in which in that case, just the limit in which the number of variables of independently distributed variables out of which you constructed the sum goes to infinity, right? So that is the thermodynamic limit. And then probably you're confused why we truncate the expansion of the exponential to the second order. Well, so that I can explain. But okay, so let us do this in private. And let me move on. So please send me an email and we'll set a time today or tomorrow to resolve this question, okay?
Okay.
All right, so what I want to do today is go back to our easy model in one dimension. So it's sum over j I from 1 to let's say n minus 1, sigma I plus 1. So it's an open chain with open boundary conditions described by the easy model where j is positive. And now what I want to do is compute. So the partition function is defined as z equal to the sum over all configurations sigma
Sorry?
e to the minus beta. Yes?
I think J has a name, but I forget.
J has a name.
Yeah.
Yeah, it's called coupling constant.
Yes.
Coupling constant. Is this the name you expected?
Yes, yes.
Good. So it's called coupling constant. So the coupling constant is positive. So this in practice is the sum over sigma 1 equal to plus or minus 1. Sum over sigma n equal to plus and minus 1. E to the minus beta j, e to the beta j, sigma 1, sigma 2, plus sigma 2, sigma 3, plus, etc., sigma n minus 1, sigma n, right? Now, notice one thing, that sigma n appears only in this last term, right? In the sum. Sigma n minus 1, so sigma 2 appears in this one and this one. Sigma 3 will appear in this one and the next one, and so on, all the way to sigma n minus 1. But the last one, sigma n, appears only in the last term, right? Because it's at the boundary of the chain. So there's only one link. So which means that in practice, I can perform the summation over sigma n explicitly, right? So I can write this as sum over sigma n minus 1 equal to plus n minus 1 of e to the beta j sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma n minus 2, sigma n minus 1 times sum over sigma n equal to plus n minus 1 e to the beta j sigma n minus 1 sigma n. You agree with me? Everybody agrees with this, right? And now let's look at this summation. Now this summation here is equal to what? Is equal to 2 cosine hyperbolic of beta j sigma n minus 1. Correct? And now the point is the following. Does this expression depend on sigma n minus 1 or not? This is a question to you.
Sorry, what's the question?
Is this expression dependent on sigma n minus 1 or not?
I think so.
No, it's not. It does not depend on the value of sigma n minus 1. Why? Because it's
or minus 1.
exactly, because sigma n minus 1 can be equal to two things, or plus 1 or minus 1. But the function cosine hyperbolic is an even function. And therefore, this guy here is always equal to 2 cosine hyperbolic of beta j, no matter what is the value of sigma n minus 1, right? And therefore, what we discover is that this summation here is equal to 2 cosine hyperbolic beta j times this summation here. But this summation here is equal to what? Someone knows what it is? It's nothing but the partition function of n minus 1 spins. This one originally was the partition function of n spins. Well, this is going to be the partition function of n minus 1 spins. You see, it's essentially the same as the one we wrote here, but instead of n, I have n minus 1. Okay?
Yes.
So therefore, I discovered the following recursion relation by doing this calculation, that the partition function
Professor,
with, yes.
Is this because of the correlation term? I mean, you're making the Hamiltonian as a correlation of I and I plus 1, and then as a consequence, you will get only the partition function of n minus 1 spins.
Well, in a sense, you're right, but you know, it's the way you say it is very imprecise. I mean, it's because of the correlation. You know, the statement "it's because of the correlations," well, should be made a bit more precise in order to have a physical meaning. That's what I wanted to say. But you're right. It's because of the structure of the Hamiltonian that is a sum of product sigma I plus 1. So the reason I can obtain this recursion is because of this structure.
I have, Professor, I have a question.
Yes.
Why don't you like separate all the term into like as the case with the sigma n minus 1 and sigma n. So we have two cosine power and d j.
Because you cannot do it. Because you cannot do it. And let me explain you why. Because you see that in general, look at sigma 2, for example. You see that sigma 2 appears in two places. Appears in this term and in this term. Right?
Yes.
And
yes.
therefore, if I combine these two guys, I will obtain sigma 1 plus sigma 3 times sigma 2. Right?
Yes.
You agree with me?
Yes.
Now you see, I can perform the summation over sigma 2, no problem. What I will obtain is 2 cosine hyperbolic of beta j sigma 1 plus sigma 3. And now the point is that sigma 1 plus sigma 3 can be equal to plus 2, minus 2, and 0. And therefore, this cosine hyperbolic does depend on the configurations of sigma 1 and sigma 3. It's not independent. You know, the reason I can write down a recursion that is so nice here is that here I did it only for the last variable, right? And therefore, yes, it's only the last variable. And
but it, yeah. But when it comes to the z n minus 1, so we have the last variable also. Just
you
one
can
time.
of course, I was going to say that. Of course, I
Yeah,
can iterate this
actually, yeah.
recursion
What I mean
relation.
is, you just separate all of the sigma 1, sigma 2, and sigma 2, sigma 3 as the way that you separate sigma n minus 1 and sigma n. Like we will have
Well, so you always
multiplication of n term.
perform explicitly the summation over the last one, right? So I'm not separating because I cannot separate in general. I cannot write this. I cannot say that Zn is not equal to the product over I of the summation sigma I equal to plus and minus 1 or of e to the beta j sigma I minus 1 sigma I. This is not true.
Oh, yeah.
This is not true, right?
Yes.
But what is true is that you can always get this recursion relation for every n. And therefore, now I can iterate this recursion relation, right? And I can say, okay,
Yes.
zeta n is 2 cosine hyperbolic beta j zeta n minus 1, which is equal to 2 cosine hyperbolic beta j squared zeta n minus 2, which is equal to 2 blah, 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 zeta n minus whatever. And at the end of the day, I will get that zeta n is equal to 2 cosine hyperbolic beta j to the power n minus 1 times zeta 1. Zeta 1 is the last summation that remains. So I always integrate over the last spin. Since I have at the end, the one before the last step is going to be the explicit summation over sigma 2, right? And this will give me again another 2 cosine hyperbolic beta j. The last term that will remain, zeta 1, is the summation over sigma 1. So what is it equal to, zeta 1?
Sorry, can I ask?
It's the partition function of one spin.
Right?
One spin, and I don't have a magnetic field.
No.
So what is zeta 1?
Is it like the cosine hyperbolic but with term sigma 2? Or
No, because that's one before the last is already included into this n minus one. So the last one is going to be just the summation over sigma one, which is going to be equal to
0.
0.
nah,
No,
Nah.
it's e
Uh,
1. E power.
nah. Guys, I mean, you said all possible numbers. I mean, you know, can be equal to 0,
No.
1, pi, minus 1,
okay.
or let's say 2. Choose
Ah,
one
I think
thing.
it's a cosine.
Oh no, please. It
There's no
cannot be
imaginary number.
It cannot be a cosine because it's not included in the list. What is it equal to? Choose a number here.
It's 2, I think.
It's 2, right? Because the last one is going to be zeta 1 is going to be the sum over sigma 1 equal to plus or minus 1 of nothing, because you know the last exponential is going to be included in the summation over is going to be eaten up by sigma 2, and therefore this is 1 and this is equal to 2, right? Because I have two
I
members
have a
of this
question.
sum.
Sorry.
Yes.
Can
So there are two questions. Who is first?
Okay, I will ask. About what you said that the n is not equal to the product of the sum.
Yes.
I didn't get why, because I think what you wrote is exactly the product of the sum of exponential beta j sigma I minus 1 sigma I. You get the question? You see what I mean?
No, I see what you mean. Well, at the end of the day, you're right. Of course, I mean, so what I'm doing here is I'm always summing over the last term. And since it's independent on sigma n minus 2, then it's fine. So in other words, I can take, you're right, I can take this summation, put it here, take the last one and put it there. And this is exactly what I'm doing. Okay? But what I was trying to say is that you cannot simply let me put it this way. This has to be done with a grain of salt, because if you didn't have, for example, open boundary conditions but periodic boundary conditions, then the fact that zeta n is at the end of the day equal to the product over blah 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 is not true, exactly because of what I told you. Because when you integrate over one guy, this one, for example, you generate an interaction between these two guys. Okay? Okay, so other question. Who was going to ask the next question? Hello?
Actually, I'm thinking, and it's almost I almost figure out.
You figured it out? Okay, good.
Yeah.
Okay, so excellent. So what we have at the end of the day is 2 to the n cosine hyperbolic of beta j to the power n minus 1. Okay? So this is our final result. Now, what do we do with this? What do we do? What do we do now, guys? Any idea? Once you compute the partition function, what should you do with this? with the partition function.
Calculate.
Calculate the
F.
thermodynamic properties.
Okay, which means compute what?
Energy.
The free energy.
Free
Okay,
energy.
so this is the answer to the question. The free energy, which is -1 over beta log of z, and it's therefore equal to minus kBT log of 2 to the n times cosine hyperbolic beta j to the power n minus 1. Okay? Good. And now, let's calculate some physical quantities. So physical quantity number 1, the energy, which is minus derivative with respect to beta of log of z. If you take this derivative, you will get minus n minus 1 times j times the tangent hyperbolic of beta j. Now, my question to you is now, is this result correct?
I don't know.
Well, of course you don't know. I mean, nobody knows. So what should you do in order to check it?
Professor?
Yes?
Oh, fine now. I've been talking, you have not been hearing me. Oh.
I didn't hear you, sorry. So do you have a question?
I think it is even fine. It's fine, we can continue.
Is what? Finite?
I mean, it was earlier at the beginning. Now I think it is a bit far from the start.
Sorry, I
She said
apologize.
the question
I'm not understanding. What?
It was, I think her question was in the beginning of the course, maybe it's
In the beginning. Okay, so you want to ask me a question about the beginning of this lecture?
I think I can ask later.
Okay, no problem. I apologize, I couldn't hear you. I'm sorry, too many people. You know what? I don't know if it's possible. Try to, you know that there is a way via Zoom to raise your hand. Let me see, try to raise your hand and let me see if I can see you. Raise your hand. Did you do this? Yeah, but I cannot see anything. Ah, no, unfortunately, when I have the, no, I cannot see it. I cannot see it from the screen. Okay, I apologize. Look,
Yeah, you have
time,
to check. You cannot. You have to check. Yeah.
Yeah, exactly. I
You
have
cannot.
to check the Zoom thing. Look, next time, stop me. Shout, stop, and I will stop. Okay. I apologize. I couldn't hear you for some reason.
Okay, just wanted to ask him another one where you said the last term was 2, just on the previous ZN.
So why I said that this is equal to 2?
Yeah.
Well, because look, Z2 is equal to what? Is equal to sigma sum over sigma 1 equal to plus and minus 1, sum over sigma 2 equal to plus and minus 1, e to the beta j sigma 1 sigma 2, right? This is Z2. Now I integrate explicitly over, I sum explicitly over sigma 2. So this is equal to sum over sigma 1 equal to plus and minus 1. And then the summation over sigma 2 gives me 2 cosine hyperbolic beta j. So this is 2 cosine hyperbolic beta j times Z1. But Z1 is what? Z1 is sum over sigma 1 equal to plus and minus 1 of 1. You see, it's the summation here. And therefore, this is equal to just 2, right? So you see how it works?
Okay, now.
Okay, excellent.
Oh, I just calculated. It's true.
It's true. Why?
Yeah. How do I say it? It's true mathematically. I don't know.
No, I understand, but I want to. So
I
don't.
think you're asking
I
about
know.
physically, right?
I know that it's true mathematically. That's correct.
Is
But
it
but
going to be
why
to take
is
another
the
limit?
exactly? I'm asking you to take limits.
Oh
So
yeah, this part I will be a little bit confused. So please go slowly.
so take the limit for temperature going to 0. What do you get for the energy? Temperature is going to 0. What is the energy equal to?
Minus n minus 1 times j.
Times j. Is this correct?
Goes to 1.
Tank 0. Oh no, tank
Sorry?
finite.
Time infinity
Finite.
is
Yeah,
1.
so is this correct or not?
Yes.
Yes, why?
Because for t goes to 0, tan hyperbolic goes to 1.
No, I don't want to know it mathematically. Why do you expect the energy to be equal to this at temperature equal to 0?
It's the minimum energy. So.
It's the minimum of energy, that's correct. But what does it correspond to physically?
Minimum of energy.
It's the ground state.
This
Okay, excellent. And what is the ground state of this?
when the old when all the bond is that between this.
So when all the bonds are satisfied, which means that all the spins are pointing in the same
Yeah, in one
direction.
direction.
Okay. So either all up or all down. In this case, all the bonds are satisfied. And therefore, this energy is minus J. For each bond, you get a minus J. Right? And then times the number of bonds, not the number of spins, the number of bonds. And therefore, you have minus n minus 1 times J. And minus 1 is the number of bonds, not of spins. And now let's take the opposite limit, temperature going to infinity. So before taking this limit in the mathematical expression, tell me what should be the energy at infinite temperature?
0.
Why?
Because it does not correlate at all.
It's too vague. I want something more precise than this. It's correct, but it's too vague. Why?
It's because all the bonds are broken, and each spin can take whatever spin they want, whatever direction they want.
Well, actually, it's not correct to state that all the bonds are broken, because a bond is broken when the spins are anti-parallel. And the point here is that at infinite temperature, you have equal probability for each pair of spins to be parallel or anti-parallel. You see what is the difference?
Okay.
Okay. And therefore, since you have equal probability to be parallel or anti-parallel, you have equal probability for each bond to contribute to the average energy with plus J or minus J, which means that essentially the average energy is going to be equal to 0. Okay?
Yes.
So this is the result. Let's now come to something else.
Oh, so it's like in the paramagnetic system where you have the.
Yes, yes, yeah.
Oh,
It's a paramagnet. It's a very nice paramagnet.
oh, what about T goes to 0? Is it a ferromagnet or something?
For temperature going to 0, the ground state is ferromagnetic.
Oh, I
All
see.
spins are pointing in the same direction. Now, what about the entropy? I'm not going to calculate the entropy. I will let you do it at home. To compute the entropy, you should take this derivative. But what I want to know from you is, once you compute this at home, what should be the limit of the entropy as t goes to infinity and as t goes to 0? So what should be the entropy? What should be this limit? This is equal to what?
0.
What should I check it against? To what?
0.
Yeah, it's
No.
this one.
No, is not equal, should not be equal to 0.
This one should be.
I know that you're thinking about the third principle of thermodynamics, but you have to think carefully here. What should it be equal to for temperature going to 0?
KB ln 2.
Exactly, K Boltzmann log of 2. Can you explain why?
There are two possible ground states.
Exactly, because there are two possible ground states, all spins pointing up and all spins pointing down. That's correct. It's perfect.
Oh, yeah.
Now, let's take the limit for temperature going to infinity. This is equal to what? Should it be equal to what?
Jonah, we cannot hear you.
I cannot hear you.
I think
K
he's
L N
trying.
N multiply N minus 1.
I don't, sorry. Can you repeat? Can you repeat, please?
No,
Hello?
I'm thinking again. Is that?
No. Maybe it's correct. Tell me again. What did you just say?
I just say it's K L N N multiply N minus 1. Maybe it's.
No, it's not.
It should be K L N to 2 power N.
So KB log of what?
2
Log
power
of
N.
2 to
power
the
n.
power n. Correct. Why?
And we have that's all the configuration that we will have.
Yeah. That is correct. I fully agree. Okay, so now the exercise that you should sort out is the following. Go back to the calculation we have just done. Take the free energy, compute the entropy, and check that these two limits come out correctly, okay? It's very important. So every time you get a result in physics, you always have to check it against some limits because, you know, people make mistakes, even mathematical mistakes or conceptual mistakes. And quite frequently, we will actually be doing making approximations. So it's even more complicated. All right, so let us now discuss correlation functions. So we have been already discussing correlation functions before. I told you that what is a correlation function is telling you essentially what is the, if I put a spin up, what is the probability, or what is, you know, how likely it is that the spin at a certain distance is going to be pointing in the same direction or in the opposite direction. So all of this can be quantified by computing the correlation function G of R, where R is the distance between spins, which is equal to sigma k plus R minus sigma k average sigma k plus R. So this is called a connected correlation function because you're subtracting the product of the averages. Okay, so all correlations are essentially connected to true correlations that are developing among the spins. And this is equal to, so if you don't, okay, so let me write it like this. If you consider sigma k plus R, this is equal to 1 over Zn sum over sigma e to the minus beta h times sigma k plus R. Now, typically a connected correlation function decays in space exponentially with the distance, with a scale psi, which is known in the literature as the correlation length. There is an exception to the statement that is when the system is at the critical point of a second order phase transition, the correlation length goes to infinity and the decay in space of the correlation function becomes a power law. But that is a special situation, right? So for second order phase transitions, psi of t goes to infinity as t goes to tc. Now, for our particular case, which is that of a one-dimensional Ising model, we already know from the Peyer's argument that there cannot be long-range order at any finite temperature. So the only possibility to have an ordered state is to go exactly to zero temperature, which means in practice that the correlation length is going to be finite at all finite temperatures. And we do expect it to be infinite only when temperature goes to zero. In other words, for the 1D Ising model, we expect psi of t to go to infinity as t goes to zero. Okay? That's why some people say that the one-dimensional Ising model has a phase transition exactly at zero temperature, but it's a rather pathological model in this respect. So don't take that too seriously. All right, so now let us learn how to compute sigma k plus R using the recursion method. Well, what we have to notice is that this is equal to 1 over z to the n, sum over all configurations of sigma, e to the beta minus beta h, and then I can rewrite sigma k plus R as sigma k plus 1, sigma k plus 1, sigma k plus 2, etc., etc. Sigma k plus r minus 1, sigma k plus r minus 1, sigma k plus r. Why I can do this? Because you see, what I've done here is I put in here sigma k plus 1 squared, sigma k plus 2 squared, sigma k plus 3 squared, etc., etc., etc. But every one of these products, since sigma k is equal to plus or minus 1, is equal to 1. In a sense, it's a resolution of the identity, as what you do typically in quantum mechanics. All right, so now I have to compute this. And now I notice that once I rewrite things in this way, well, I have pairs of spins which are nearest neighbors here, right? I have a product of pairs of nearest neighboring spins. Okay, so now to compute this object, I can easily operate as follows. Let me generalize my model, my easy model, to something like this. Instead of h being minus j times sum over I sigma I plus 1, let me make the coupling constant dependent on I. So let me write it as minus sum over I, ji sigma I plus 1. Now, the other model they wrote down before is when ji is equal to j for all I. That's a special case of this one. And now for this model, what I have is that my partition function Zn is going to be equal to the sum over sigma e to the beta sum over I, ji sigma I plus 1. And you can easily convince yourself that also in this case, you can use the recursion method to compute the partition function. And what you will get is 2 to the n product over I from 1 to the power n minus 1 of cosine hyperbolic beta ji. Now you see that this is exactly what I had before if I put all the ji identical, right?
Professor.
Yes.
I'm really sorry, but can you re-explain again how you get the definition of correlation function? I mean the sigma k plus r.
It's just a definition.
Oh,
So I didn't get it. I just defined it.
oh, it's just defined. Oh, it's not
Yeah.
derived or something.
No, it's not derived from anything. It's just, I say that this is the correlation. Everybody says this is the correlation function.
Oh.
So it's the average of products of spins at two different space points.
Okay.
Why to use this average of products of spins? Well, that you understand very well. If I know that this average is positive, right? I know that my spins are correlated. Why? Because if one spin is pointing in one direction, the other one at a certain distance is going to be with high probability pointing in the same direction because the correlation function is positive, right? If instead it's negative, then if one spin is pointing in one direction, while the other spin at a certain distance is most likely going to be pointing in the opposite direction. You say that they are anti-correlated. And if it's equal to 0, or it becomes very small, if my spin is pointing in one direction, the guy at a certain distance doesn't care about what the spin is doing and will be pointing with almost equal probability up or down. Okay? So the value of the correlation function gives me information on the correlation between the spin at position k and the spin at position k plus r. That's how it works. Is it clearer now?
Yes.
Okay, so let's move on. So now, how do I compute this correlation function? Sigma k plus r. Well, you see, I can simply notice the following. Let me put it here in. I notice that if I take a derivative of Zn written up there with respect to beta ji, what I obtain is sum over sigma e to the beta h times sigma I plus 1, right? If you take a derivative with respect to beta ji, you take down this product. Therefore, in order to take down all these products, I take a derivative with respect to beta jk plus 1, beta jk plus 2, up to beta jk plus r minus 1, right? So this is going to be equal to the derivative with respect to beta jk, derivative with respect to beta jk plus r minus 1 of Zn divided, of course, by Zn itself. So it should be the derivative of the log. Now, if you take this derivative, look at this expression. So for all the terms in which you have the derivative of the cosine hyperbolic is the sine hyperbolic, right?
Professor?
So, yes?
Okay, Jonah has so many questions in the chat, you may check.
Who has a question?
They're in the chat,
Jonah.
in the chat.
In the chat. Oy, oy, oy. Jonah. 0, no disorder. Is correlations always pairwise? Is correct? Well, no. You can compute multi-point correlation functions. This is actually called the 2-point correlation function. But you can compute correlation functions of 3 spins: sigma I, sigma j, sigma k. Or you can compute correlation functions of 4 spins. You can do whatever you want. I mean, this gives you information about different structures that you might have in your system. But typically, if you want to characterize a second order phase transition, it's just enough to use the 2-point correlation function and nothing else. Okay? So now, let's take all these derivatives. I will get 2 to the n. Well, then I will have the product over all I from 1 to k minus 1, cosine hyperbolic of beta ji. Then the product over I from k to k plus r minus 1 of sine hyperbolic beta ji, and then the product over all remaining spins from k plus r minus 1 to n minus 1 of cosine hyperbolic. And then you have to divide everything by 2 to the n product of cosine hyperbolic for all bonds. Now you see that the only ones, I mean, these ones will be gone. These ones will be gone with the equivalent ones downstairs. And what will remain is, at the end of the day, this goes with that, is product over I from k to k plus r minus 1 of the tangent hyperbolic of beta ji. Okay? And now I want to use this expression to compute my original correlation function for the model in which all ji were equal. So let's take ji equal to j for all I, in which case this is nothing but tangent hyperbolic of beta j to the power r, that I can rewrite as exponential of minus r over psi, where psi is equal to minus 1 over the log of the tangent hyperbolic of beta j. And now, what happens when the temperature, well, when the temperature is finite, tangent hyperbolic is a number between 0 and 1. The log of that number is going to be negative, and therefore the correlation function is good. The correlation length is going to be positive. So there is nothing wrong about that. Now, the question is, what happens when the temperature goes to 0? Now, when the temperature goes to 0, the tangent hyperbolic tends to 1. The log of the tangent ln, I mean, this is I always write it as log, but I know that you don't like this. So it's a natural log. The ln of the tangent hyperbolic, it goes to 0, and therefore the correlation length goes to infinity, actually plus infinity, because the tangent hyperbolic is always less than 1. And therefore we discover that in practice, we always have a finite correlation length with an exponential divergence as t goes to 0. Okay? Are there any questions about this?
Oh, so it diverges.
Yeah, it diverges as t goes to 0. The
Okay.
limit for t going to 0 of chi is equal to plus infinity.
Oh, because the logarithm of tangent is 0.
Yes, exactly. Okay?
Why is it not minus infinite?
Because the tangent hyperbolic is always less than 1, and therefore the log of the tangent hyperbolic is always negative.
Oh,
The log of a number smaller than 1 is a negative real number. You agree with me? The tangent hyperbolic is between 0 and 1, and the log of the tangent hyperbolic is always negative,
yes, yes.
right? So,
Thank you.
okay, so this goes to plus infinity. All right, so now let us, after dealing with the easy model, let's deal with another model that is actually quite interesting. That is known as the Potts model. Potts model. Have you ever heard of the Potts model? So the Potts model is actually defined as follows. Suppose that I take a variable, sigma, that instead of having two values, plus 1 or minus 1, has q values, q possible values between 1 and q. Okay? And then let me define my energy function, my Hamiltonian, as sum over ij delta sigma I sigma j. So if the two variables are identical on neighboring sites, then I get a contribution to the energy minus j. If they are different, I get 0. Okay? Now, you should think of this as if in practice your Potts variable is something like this, is like a spin that doesn't have just two positions, up or down, but has many positions in space. And the way you minimize the energy between neighboring spins is you say, okay, if the two are parallel, then I get a contribution to the energy minus J, but if they are not parallel, it gets 0. That's why sometimes people call this, in particular in the quantum context, clock models, because it's like having a clock. A digital clock in which the positions of the
Professor.
Yes.
Did you just say about if the spins are parallel, it's minus J, and not parallel, not anti-parallel?
Well, if they are not parallel, so they are pointing in different directions, the energy contribution is 0.
Also, whatever angle it makes.
Whatever angle.
Yeah.
So that's, if you look at this Hamiltonian, whatever angle the contribution of the energy to the energy is equal to 0.
Sorry, but judging from your picture, you have only anti-parallel spins.
What do you mean? So
I
these
mean,
are all the possible directions of one spin.
Oh, yeah.
For Q equal to 1, 2, 3, 4, 5, 6, 7, 8. For Q equal 8.
Oh, okay.
That's how I imagine it.
But what will happen if you have many of these possible?
Well, so I mean, it becomes harder and harder to visualize, but in practice, you should think no matter what is Q, if two neighboring variables have the same value, then the energy is so then the two guys are parallel. Sorry, then the energy is minus J. If they are different, then it's 0. It's very simple. You can visualize it in many different ways, right? One way you can visualize it is on any sides, imagine having.
I'm sorry.
Yes.
Is it delta function? Delta
Is it?
I mean.
Is a Kronecker delta. This is a Kronecker delta. Kronecker.
Okay.
Okay, so you can visualize it as follows. On any side, imagine that you have Q possible values that you can have. And now, if two neighboring guys are on the same level, right, then you get an energy minus J. If they are on different levels, like this one and this one, you get 0. They don't interact. They interact only if they are on the same level. That's it. Of course, I mean, this kind of Hamiltonian will tend to favor configurations in which all spins are pointing in this, all variables are at the same value, right? Because that's what minimizes the energy. Correct? All right. So now the easy model has Z2 symmetry. What is Z2? Z2 is the symmetry under inversion. So if you set every sigma I for the easy model into minus sigma I, you get the same energy. What is the symmetry group for the Potts model? Do you know what is the symmetry? What could be the symmetry of this Potts model? For the energy, what matters is two variables being equal or being not equal. It doesn't matter what value they have, right? That's the only thing that matters, if you're equal or you're not equal. Therefore, if I take my variables, let's call them 1, 2, 3, 4, all the way to Q, and change names to all of them. So for example, perform a permutation in which this 2 goes to 1, 1 goes to 2, 4, 3, etc., etc. Any permutation will leave the energy invariant, because what matters for me is if two neighboring variables are equal or not. But if they were equal before the permutation, they will be equal also after the permutation. If they were different before the permutation, they will be different also after the permutation. If I apply the same permutation to all sides, of course. And therefore, this is a symmetry. So the symmetry group of this guy is not inversion like Ising, but is all possible permutations of Q elements. All right, so now what do we want to do? We want to compute the partition function for this Potts model. The partition function is going to be the sum over all configurations of my guys, e to the beta j sum over I from 1 to n minus 1 delta sigma I plus 1. And now I use the same recursion method as before, right? So I have that this is equal to sum over sigma, sum over sigma 1 equal to 1 to q, etc., sigma n minus 1 from 1 to q, e to the beta j delta sigma 1, sigma 2, plus delta sigma n minus 2, sigma n minus 1. And then I will single out the summation over sigma n equal to 1 to q, e to the beta j delta sigma n minus 1, sigma n. And now what I would like you to figure out is what is this summation equal to? So what is this stuff equal to? This is equal to what? Let me help you. Imagine that sigma n minus 1 is equal to something, some number between 1 and q. It doesn't matter which one. And now I'm summing over sigma n.
N minus 1 plus e j e power bj.
Well, the n minus 1 is, no, why n minus 1? So
because we run from 1 to q, so we have we may have we may have the with the exponential part, we may have the result is 1 when we have the same spin, and when we have different spin, and
yes.
it
will
what? Be e power bj when we have same spin. But
when we have the same value, we have e to the bj.
Yes.
Right? How many ways do we have to have the same value? One, right? Because sigma n minus 1 is given. Sigma n minus 1
only
is
one.
something. So there is
I
only
think only
one
one.
way.
Yes.
Yes. Plus,
And
and
plus
then
n
when
minus one. N minus
no,
one.
wait, why n minus one?
Because you have n minus one other
No, it's
choice
not.
to be different.
It's not n minus one. It's q minus one.
Ah, run to one to q. Okay. Yeah. Yeah, I
So
see.
times q minus one times when they are different, I have e to the beta j times 0, which is 1, right?
Yeah.
So overall, I will get e to the beta j plus q minus 1, right?
Yeah.
You agree?
Yes.
Okay. So therefore, I discover in this case that Zn is equal to e to the beta j plus q minus 1 times Zn minus 1. And now I go on, I iterate this recursion relation, I will obtain that Zn is equal to e to the beta j plus q minus 1 to the power n minus 1 times Z1 as before. Now, what is Z1 equal to in this case?
Q.
Q, correct. So this is Q times e to the beta j plus Q minus 1 times n minus 1. All right, so we computed the partition function. Okay, so now, well, once you have given the partition function, you can compute the free energy, which comes out to be minus 1 over beta log of Z. You can also compute the internal energy, which is minus d beta log of Z. Now, I'll let you do it at home. So just do it yourself. You will get minus n minus 1 times j times e to the beta j divided by q minus 1 plus e to the beta j. So this is the result of the calculation. All right, so let's take the limits now. Limit for t going to 0 of this expression of u. What is it equal to? For t going to 0.
Zero.
No. No, it's not equal to 0.
It's minus
Minus
n
n minus
minus
1 j.
minus n minus
Minus
1
Yeah,
Minus n minus 1 times
J.
j. Okay, so is this correct?
Yeah, because it's the minimum value.
Yeah, it's, at 0 temperature, all variables will be the same, right? All spins will be pointing in the same direction. By the way, how many degenerate ground states do you expect to have?
8.
What?
Is that it because you're 8 because in your
Well, 8 if q is equal to 8. In general, for general q, how many?
q.
Q, correct. So you will have q degenerate ground states. Let's see now, what about limit for t going to infinity of u? What do you get?
K logarithm q. Oh.
What?
Oh no.
Zero.
Sorry.
0.
Yeah, 0.
0, 0, 0. It's
No,
zero.
you don't. No, 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 no. Let's first take the limit of the expression. You see, I caught you. That's the point. You have always to use your head. Take
It's
the
1
limit
over
of the
Q
expression first. What do you get?
1 over Q minus
1 over Q
minus 1 times N
So
minus
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 n minus 1
J,
times J
J over Q.
divided by Q, right?
Yes, Q.
Now my question is this correct?
Mm,
Hmm. Maybe.
So yeah, it could be. I mean,
I mean, does Q like?
that's always a correct answer, right?
I mean, you have Q.
There's
Let's
also
say it's
another one that is always correct sometimes.
okay. So
Okay.
actually, I'm thinking since you have Q degenerate ground states, I mean, you also have like Q variation. You have to divide by the Q variations to get the correct energy. I don't know.
Yeah, but
Don't
again,
mind me.
this is not precise enough. Is this correct? Again, it's not equal to 0. You see, you expected it to be equal to 0. It's not equal to 0. It's actually different from 0. Is this correct? Let's think slowly. Before it was equal to 0 because you had equal probability for neighboring spins to be parallel or anti-parallel. Okay.
Oh, because in this case we have different probability to be in the same and different. We have more case to be different. Like we have
Kind
more.
of. You're almost there.
Um.
You have certainly more cases to be different. That's fine. So each spin, in this case, each couple of neighboring spins has one way to be parallel. You know, if you fix the configuration of one of them,
yeah, and
there is
minus
one way
Q
to be
minus
parallel,
1 to be different,
and then Q minus 1 to be different. And 1. Now, if they are parallel, the contribution to the energy is minus J. If they are different, the contribution to the energy is what? If they are different, the energy?
0.
Contribution to the energy is 0, correct. So now for each bond, the average energy is what? Is minus J. If all these configurations are equally probable, the average energy is going to be minus J times 1 plus Q minus 1 times 0. And then, since I'm computing the average energy, I should divide by the total number of configurations, of possible configurations, which is Q, right?
Yes.
Yeah, and you sum over all n minus 1 interactions.
Exactly, and then you sum over minus n minus 1 bonds. So the average energy per bond is minus J over Q times the number of bonds, which is n minus 1. So you see, everything is correct, apparently. Okay? And now, another exercise that you could do is compute the entropy, which as usual is minus df dt. And now if you compute the entropy, what should be the limit for t going to 0 of S? Okay, Boltzmann
K
times
logarithm
log of Q, because I have Q degenerate ground states. Well, the limit for t going to infinity of S should be equal to KB log of
Q to the power of n minus 1.
N minus 1.
no, actually Q to the power
N.
N,
Q to power.
right?
Yes.
Because you would, so don't get confused. Here you have to put the total number of configurations that have a certain energy, right? That have a certain or consistent with the macroscopic conditions. If you have infinite temperature, all configurations of the system are equally probable, right? How many total configurations has my system? Q to the n, not Q to the n minus 1, right?
Okay. Yes.
So this is the total number of configurations. So you see, statistical mechanics is a tricky business because it's simple, but you have to think carefully. Every single time you do a calculation, you have to think carefully about what you're doing. All right? So there are details and all kinds of things that you have to think about. All right, so we're done for today. I invite you, please, to go through, I mean, essentially you have to take derivatives and take limits. So please do it by next time. So you have a couple of days and you don't have to take buses, you don't have to travel, you don't have to do anything. You're staying there at home. Please do these 2 calculations. And next time we're going to do something called a transfer matrix, which is a very general and important way to compute partition functions of models described on defined on a lattice. Okay. Yes.
Professor.
Yes.
Yes.
Are you asking us to calculate all the limits you have shown the result?
I'm just asking you to fill up all the holes in these lectures. For example, here, this calculation, I just wrote the result, but I haven't done it, right? The entropy I never calculated and I never took the limits. So please check the limits of the entropy.
Okay.
Right? And the same here for the here, right?
Yes,
For
yes, it's true.
compute the entropy, fill up all the limits, do all these calculations, and check everything. Okay?
Okay. Actually, Jonah has a question again in the chat.
Just let me see the question. Shoop. Does the POTS model have any physical applications? Okay, it's a complicated issue. Yes, it has physical applications, but the problem is that in order to explain what are the physical applications, I should explain you what is a universality class. And it's too complicated. So in short, phase transitions in different systems can be classified according to something called critical exponents. And it turns out that different systems can have the same critical exponents. For example, the liquid to gas phase transition, when it becomes second order, so at the end of the first order line, has the same critical exponents of the easy model. So, and when they have the same critical exponents, you say they are in the same universality class. Well, it turns out that the POTS model is identifying another universality class, which is more general than the one of the easy model. So the short answer is yes, it has applications because there are many systems that have this kind of symmetries, because what is important are the symmetries for the universality class. But I understand if you think that, you know, as a spin model is not very realistic. True, I'm not saying it is. It has applications because there are other systems that actually have these symmetries. So have a permutation symmetry as fundamental symmetry of the Hamiltonian. They are sitting in the same dimensionality as the Potts model, and therefore are sitting at the same universality class as the Potts model. It's a bit complicated. I'll try to explain you towards the end of the course if I get there. Okay, it's a rather important, very important issue connected to things called renormalization group and so on and so far. But it's too advanced for the moment. So for the moment, let's keep it as a work of imagination. But I just told you it's not just a work of imagination. It's important. Other questions?
Professor,
Yes.
you said that we can fix some time to discuss some questions, some of my questions.
Yes.
When you can do it, or
would it be okay to do it? Well, this afternoon I'm rather busy. Can we do it on Friday before the lecture?
oh, like how? Yeah, how many hours or minutes before the lecture?
Well, half an hour.
Okay.
Would it be okay? I mean, you need more? You know, in the morning I wake up at 5. If you want to, you know, we can connect at 5:30. If you have a
Yeah.
lot of questions. I mean,
But how do I contact you?
I will send you. Well, that's an interesting question. Drop me an email, so you know what is my email.
Is it
I will write it in the. I will write
Sisa?
it in the chat.
Okay.
Silva@sisa.it. Drop me an email and I will send you a link. Okay?
Hello.
Okay.
Yes?
Can you share with, I mean, all of us the link if someone has
Yeah,
questions
I will
also
send
can
you to
join
your
in.
colleague and he will
Yeah.
send it to everybody. Okay?
Thank you. Thank
No
you.
problem. Okay, good. Okay, so I'll see you on Friday then. Okay?
Okay,
So
bye-bye.
please drop me an email. Bye-bye.
See you. Okay. Guys, are you there? Hello. Yeah, I don't care. Actually, I just want to talk about a few things. So, like, please don't talk over the professor, or yeah, and please mute your mic after you speak so we don't have some problems during the meeting. Yeah, just to remind that. I bet you already know, but yeah, I just need to remind you that again. Thank you, guys.